welcome to the third part of this lecture, and now we will talk about speech perception. Sorry, speech production, of course. Okay, let's have a look at this graph, which shows the cycle, everything which is involved in producing speech, and it starts in the brain that we get the idea of what we want to say, what verbal message, vocal sound we want to produce. This is then converted into activity, neural activity, so that muscles change the volume in the lungs so that we get an airflow, and the vocal folds then can control the way we speak. And then we have the vocal tract, which at various places can shape the airflow so that we have different sounds in the end which we can produce. And this is then produced in the form of air waves and an acoustical signal. And in the next part then we will look at the perception of those parts. So let's have a look at a little bit more simplified version. When we produce speech, we use a combination of organs, which we see here in the figure. So we have the larynx, the vocal cords, then the pharynx here, the back of the throat, the palate, we use the tongue, we have the teeth, we use the lips, and things like that. And when we have phonemes, if you remember the first part, so the smallest acoustical units which bring about a change in meaning, then these phonemes can be classified by two aspects in the way they are articulated. The first one is the place of articulation. That means where in the mouth is the airflow obstructed. And to understand that, if we do not obstruct the airflow, then we just have a breathing sound, like only by modulating that airflow, and modulating in the widest sense we can say obstructing it, we produce a sound. So, for instance, in the TH, I put my tongue behind the front teeth and then get this TH sound from that. So the obstruction then is in this area, as an example. Another example is we have so-called plosive sounds, where we put up a pressure and then release the pressure suddenly. So in the P, when we produce the letter P, like in pressure, we close the lips and then we release it. So the place is the lips, and if we have the letter T, we put the tip of the tongue roughly here, we build up the pressure and then we release it, T. And if we do the K sound, then we put the tongue up somewhere here, build up pressure and then release it. So you can see these different places of articulation, P, T, K. Just try it yourself to see the difference. And then we have the manner of articulation. How is the airflow obstructed? And for instance, when we produce a T, then we put the tongue roughly in this area and obstruct it completely, while for the TH, like in think, we also put it similar, slightly different position, but air is still allowed to flow through here. So it's different ways of obstructing the airflow. And then we have as a third parameter, we have the phonation or the voicing. So for instance, we have the S, the unvoiced sound, and we have Z as the voiced sound, which are similar with that. Okay, so this is how we can try to describe speech by means of phonemes, and how these phonemes are created by where we obstruct the airflow, the place of articulation, and how we obstruct the airflow, the manner of articulation, and whether it's voiced or unvoiced. To describe the acoustical signal, I would like often something which is called a spectrogram is used, and to understand a spectrogram I would like to have a brief detour to explain what a Fourier transformation is, because that's the basis for a spectrogram. If you don't fully understand this, what we are doing now, don't worry. It's not relevant for any assessment, and it's not totally directly, or it's not linked to cognitive psychology as such. Suppose we have a signal like that. It could be a recording of a speech or of a music or any other sound. This, what I describe, can be done for any acoustical signal. Now, when we have such a signal, we could try and describe it as good as possible by breaking it down in sine frequencies. And when we do that, we may see, oh, this complex signal is actually just an overlay of these three signals. It's a rather slow wave, so it would be a low-pitched sound, and a wave with a higher frequency, so a middle pitch, and then a high frequency. So if you just overlay these three over each other, you get this one. Now, a Fourier transformation tries to do this, tries to find out, when I have this signal, which frequency components, low, middle, high frequencies, are in there. So what they would plot is, here is the frequency, and here is the amount of energy in each frequency. In this example, we have these three. The low frequency would be this bar, the middle frequency would be this bar, and the high frequency would be this bar. And if we would have something in between, it would lie here. Now the height of the bar would reflect the amplitude. That means basically the loudness of the signal. So they are all the same here, but suppose this one would go up here and down here and up here and down here, then this bar would be higher. It's louder. It contains more energy. Now what we have here is a representation for one point in time. But most signals, in particular speech, they vary across time. So the frequency components we have in the signal at any moment of time differ. So what we can do is we convert that graph into, or we have this signal across time with a high frequency, middle frequency, and low frequency, and then we get this diagram across time. This would be the normal signal as we know it from a wave editor or something, and this would be the representation of the frequencies. And usually we have a lot of other frequencies in there as well, so you would get a lot of noise here too. Now what we can do is, in a spectrogram, we represent the amplitudes and the frequencies by some color code to put even time in there. This is the standard waveform. So here we have amplitude, and here we have time. So this could be one word, 2 words, 3 words, something like that. And the spectrogram would look like this. So what does that mean? On the x-axis we now have time from left to right. So we say something here, so there is something going on here. I will explain that in a moment. Here as well, and every time we have silence we have here. On the y-axis we have the frequency. So down here we have low frequencies, and up here we have high frequencies. And the color now, or the shading, shows how much energy there is. On the previous graph, where we said we have these peaks, how high the peak is. The higher the peak, the more energy, the higher the amplitude, the darker it gets. You can see that here where it fades out and the amplitudes are low, it gets bright, and where we have a lot of energy, it gets dark. So we see we have a lot of energy down here in the lower frequencies, and less energy in the higher frequencies. So that's how a spectrogram looks like, and the spectrogram is one of the key representations of the acoustical signal for people who work with speech and language and want to analyze the acoustics of that. And it's also one approach for computers to understand and process language, to do such a Fourier transformation and then analyze it basically like the human does. Okay, so this is a different one where the idea is the same. We have time, we have frequency, but now it's color coded. What was as gray and dark grayish as before is now and black is now red, and where there's little energy it's blue. And what we see when we analyze language is that there are bands of energy in certain frequency range, and these bands are called formants. And it's interesting to note that with these formants, here's an example, and the lowest one, it's often called also either F0 or the fundamental frequency, which kind of determines the pitch of the voice. And by these formants, here is another one, here is another one, and where the formants are, in which frequencies they have and how they change across time, helps us, or is the way how humans decode language. And just the formants determine which vowel we hear. So the E has a low F1, the fundamental frequency. Sometimes it's called F0, some people start counting at 1. And here's the F2, so the second formant is up here, and there's a large gap between that. This is again time, and this is the frequency. You see 1000 Hertz, 2000 Hertz, 3000 Hertz. The U has a low F1 and also a low F2. The R has a higher F1 and also a low F2. So just by determining this very pattern. So suppose you have such a complex speech signal, and all you need to know in your analysis, you can make it so abstract to say F1 roughly around 500 Hertz and F2 very high. F1 low, F2 low. You can already say, okay, that must be an I and that must be a U. And this is extremely powerful and makes us able to understand people with so different voice characteristics. Some has a deep voice, some have a high-pitched voice, we have accents and things like that. And this very high-level abstract processing makes it possible to ignore all these individual abilities. Okay, so these are different spectrograms. And what we see here is that the words, first two, start with ball and bar, and what we see is that they all start similar with the R sound, but then the L and then the R goes down here. So we see that the change of formants across time is informative to see what word it is. What's also interesting to see is here we have bow, and we have a different sound here after the B, and we see that we get a different formant here while it's higher here. Okay, before we go to the summary, I would like to actually do a little practical demonstration of a live spectrogram to show you how it looks like. I hope it does record properly with our recording software which we use for these lectures. Let me restart that. Okay, and now you will see what happens. We get a live spectrogram. So we have the time here again, Here we have the frequency on the y-axis, and the shading is that blue, so black means there's only very little energy, and blue means that there is more energy, and it gets as brighter as the more energy there is. And I will try to demonstrate that now so that it hopefully becomes a little bit clearer. And a good way to demonstrate the very basic principle is to use whistling. So I will now whistle a little bit and you can see what happens on the screen. So you see that the spectrogram shows you the energy you have, the frequency of the energy in the signal. I will also try to illustrate that the louder you get, the more intense it gets by producing an A and R vowel sound. However, I'm not very well trained in this, so when I get louder, I tend to get slightly higher in the pitch as well, so that the energy band goes up a little bit. Please ignore that. What I want to demonstrate you is the intensity, that the loudness, the energy in the signal determines the intensity. So let me try that. So you see that where I was loudest, it gets brightest here. That's the idea of how to encode the amplitude or intensity. And now, as we've seen before, you already see these very, very prominent formants here. I will just show you different vowels, how they look like. So let's start with the R again. Okay, I'm not quite sure. I should have maybe chosen a slightly different scale here, but the differences are a little bit harder to see than I expected. You can see that here the frequency is a little bit higher. You can see that the energy distribution is a little bit different. So let us try that again so that we can just focus on no, I just want to stop. So we reduced that quite a bit, and maybe we can also, change the speed a little bit? Okay. So now the signal should be a little bit stretched, so we have a lower signal here. Let's try that again. Here you can now see, for instance, that the E has a higher. It's still, I don't know, doesn't come out perfectly. Maybe I have to increase the resolution. We will keep it at now. By the way, this software is called Spectrogram 16, and you can find that if you search around. I may have to stop that. Stop. Yes, here. If you Google for that, it's a really nice thing to do these live spectrograms And to do that, it's an old software, I think, but it still works perfectly well. And there's also a version around which you don't need to actually install on the computer, and you can just run it on in the Windows software. Okay, so is everything all right back? Yep. So to summarize this part, we've seen that the production of speech is a complex physiological process where several organs in our vocal tract interact with each other to produce the sounds we want to produce, and we can describe the sounds by the place and manner of their articulation. And these spectrograms, which we played around with a little bit, are used to analyze and represent the speech signal. And if you're trained in that, a lot of people just look at the spectrograms and can derive so much information from them and understand the signal. If you have any questions, as usual, please go to the discussion forums on BBL and post them there.